Living requires energy. People have always been interested in moving, heating, and cooling things. But before the invention of machines, the only power available was animal power. The invention of the engine transformed how we live, allowing people to travel, communicate, and control their environments in ways they never had before. These changes and developments happened because of engines that require fuels like gasoline, petroleum, or oil. But fuel is not the only source of energy around. I'm Science Mom.
I'm Math Dad.
And today we're going to explore the history of some of our most important industrial inventions. Hello! A special welcome to Victor watching from Belgium, to Luke and Isabel watching in California. I see Savannah and Finn. Welcome everybody. Today we are going to be talking about energy. And I think it's worth starting off with just asking the question, what is energy?
So energy is the ability to do work, right?
It is. It's the ability to make things happen, to move, to heat something, to cool something down. The ability to make something happen, that is energy. The ability to do work. And in the United States and in Canada, over the past couple weeks, we have had an incredible wave of cold weather. And there's nothing like when it's cold to help you appreciate just how much we appreciate having it be warm. And back in the day, the only source of heat that you would have in your house would be a fireplace.
Oh, yeah.
And some of you
We don't even have a fireplace.
We don't have a fireplace in our house. Some of you watching might have a fireplace in yours, but it's more common for us now to rely on electricity as our source of power. Today, we're going to explore several of the different types of ways that we can produce electricity.
So I know it's been really cold. One of our class members, Pickle Obsessed, even did a little experiment that we thought we would share with you guys.
Did you know that if it is really cold, you can take boiling water and turn it into snow?
Oh.
Isn't that awesome?
So that was boiling water?
Boiling water.
And she threw it up in the air?
Toss it into the air. And it was minus 10 degrees. And so that all those water droplets froze and essentially just turned into snow. So if you are up in Minnesota and Canada and we have another cold wave like that, that's a cool experiment to try. Make sure you're careful though with taking that boiling water out and tossing it. Awesome. Thank you for sharing that with us, Pickle Obsessed. We thought that was pretty cool because that's not something we can do here in Nevada. Our weather here has been a lot warmer. But
I'm kind of glad too, though. I don't like it when it gets that cold.
But let's get back to talking about power, because nothing makes you appreciate power more than when the power goes out. And that happened for millions of people in the state of Texas this last week. I remember, Math Dad, the first time that I had a power outage, I was a kid. I think I was about 10 years old. And I went downstairs and my mom told me in the morning when I was getting ready to eat breakfast, she told me the power was out. I opened up the fridge to get a glass of milk. And she said, careful, we only want to open the fridge once or twice today because we don't want everything to warm up. So I closed the fridge right away. And then I thought, well, I'll microwave myself some oatmeal. Went to open the microwave and then remembered the microwave doesn't work. And I said, no problem, I'll get myself some toast. Opened up to get the toaster and realized the toaster doesn't work. And then I realized the stove and the oven didn't work either. And I thought, how am I going to make myself some food? I can't heat up anything.
Whoa, yeah, we really rely on electricity for power.
We really do. And the way that we get that electrical power, a lot of it comes down to magnets.
Magnets?
I'm not kidding. This is really kind of cool. So I have a flashlight here. This flashlight is a crank-powered flashlight. It's an emergency flashlight. It does not have AAA batteries in it. It gets its power by somebody turning a handle. So if I turn this, the flashlight turns on. But when I stop spinning, it goes off.
So you're saying there are magnets involved somehow?
Yes. If you spin a magnet, that creates a current of electrons, which then can be captured and put in a wire and used as electricity.
So that's how electricity is made?
This is how electricity is made in so many different ways. So this is one way in a flashlight. But let's talk about a power plant. because coal power plants and natural gas power plants, those produce most of our energy in the United States. About 62% of our energy is going to come from burning coal and natural gas. So what are we doing when we burn coal and natural gas? Are we just burning it in like a big fireplace and that's it?
Are we using the heat to somehow get the energy?
We are using the heat to boil water and make steam, and then that steam is going to spin big magnets.
So wait. You're saying when we burn coal, there's like a science mom arm or math dad arm that's getting our power?
In a sense.
Because of the steam.
In a sense. And actually, the way that a coal or a natural gas power plant and a nuclear power plant works is pretty similar. Both of them are going to have some sort of a source of heat, and then it's going to heat water into steam and cycle that water around, spin big magnets in a generator, and that's going to create electricity. That is essentially what is happening in a coal power plant, natural gas power plant, or a nuclear power plant. We're heating up water, changing it into steam, and then using that steam to spin magnets.
One more time. Let me look at that. So off on the left is where we're getting all that heat, and it's sending the steam that spins the turbine, which is spinning the generator with the magnets, and that's where we're getting our power.
Yep.
Just like this flashlight is a mini
power
plant.
A lot like this flashlight. This flashlight really is kind of like a mini power plant. But the thing with coal and natural gas is that they are not renewable. So that means that once you have burned up your coal, you're not going to get more coal unless you go to the ground and dig out more coal. And renewable energy sources, that means that that source of energy is something that's going to come back again and again.
But wait. With coal, if we just wait a couple hundred years, won't there be new coal in the ground?
No, our fossil fuels, things like petroleum, natural gas, and coal, they actually take more than 50 million years to form. Most of them are 300 million years old. They're from the Carboniferous period.
Oh, wow.
That is a long, long time ago. So we're going to talk about the 5 main ways that we get energy in countries like the United States and Canada and Belgium and Italy and the UK. All of the developed countries, they get their energy from, number 1 is fossil fuels. We talked about burning coal. Number 2.
So, and you said petroleum. Is that the same as just saying oil? Is that made from petroleum?
Yes. Okay. So we can use those terms independently.
Interchangeably, essentially?
Yeah.
Okay.
So coal or fossil fuels, that's the first one we talked about. Our next one is wind. So when we say wind, we're talking about turbines, windmills that spin around in the air. And what do we do with that spinning motion?
Is it spinning magnets?
Yes, we spin magnets. Now, the advantage of a windmill is that we're not producing any pollution. It's quite clean. The disadvantage is we can't control when the wind turns on or turns off. So sometimes it might be really windy and you get a lot of power. Other times it might not be as windy. You will get less power. So it's intermittent.
So we say it's renewable, though, because we're not using up the wind. There will always be more wind.
That's right.
Connor asks, is charcoal renewable?
Any type of fuel is considered not renewable because if you burn charcoal or like a wood fireplace and you burn a piece of wood, you're actually changing that initial source of energy. You're changing it into something else.
So once you've used it, it's gone.
You're using it up and it's gone.
Gotcha.
Next type of energy that we're going to talk about is solar power.
So solar power means power from the sun.
Power from the sun. And solar panels are pretty amazing. When you look at a solar panel, the solar panel is capturing light and then it's converting that light into electrons. And here we're not spinning a magnet.
Oh, so this is a different idea, different process.
It is. And there's a misconception. Some people think that solar panels need to be hot to work. They don't need to be hot. They just need to be in bright conditions. In fact, living here in Las Vegas, if I have solar panels on my house, they work a little bit better in the cooler months than they do in July when it's 115 degrees Fahrenheit. If the panels get too hot, then they're not quite as efficient. They still keep working, but they work best when it's a little bit cooler. And they work just fine in the wintertime as long as there is sunlight. So if your solar panel is covered in snow, is it going to work? Well, no, because it's not getting light.
Yeah.
But if it is below freezing, but your solar panel is getting sunlight, it will still be producing electricity.
Okay, so the advantage to solar power, it's renewable. We're not going to run out of the sun anytime soon, but you're kind of at the mercy of the sun. So if you live in a place that has shade all the time, you're going to get a lot less power.
You won't get as much power. And do you get power at night?
Oh, definitely not.
No,
So
unless you have a really good battery. And a lot of solar panels now, they come with a good battery that gets charged all during the day. And then at night, you still have power because you're just pulling the power from the battery. But you have to store that power somewhere because at night, the solar panels aren't getting light. And there is another type of solar power that is actually pretty amazing. And this one is not very far from where we live. Instead of having solar panels that are taking that energy from light and are converting it into an electron that gets put into a wire, this takes mirrors and uses sunlight to boil water. If you ever drive from Los Angeles to Las Vegas, there are 3 towers that look just like this by the freeway before you cross into Nevada. This is an amazing and huge tower that has a boiler up top. And these mirrors are being pointed so that they focus the sunlight at that tower and they boil the water to more than 500 degrees Celsius.
Oh, man.
It's an incredible amount of heat that is produced. And then that steam, just like in a coal power plant, just like in a nuclear power plant, that steam goes and
spins magnets.
And that's what makes electricity.
Whoa. So that is a really clever use. So just a mirror is not very advanced. We've had mirrors for a long time, and you just have to make sure that it's pointed in the right direction. So,
and they move throughout the entire day. So these mirrors actually have pretty sophisticated little computer and sensors that track them, and they move throughout the day to get as much sunlight as possible. And the mirrors are very shiny and reflective. If you duck down real quick, Math Dad, see that?
I see that.
So these are, they almost look like they blend in with the sky. Those are 2 mirrors on top of the truck as they're building this facility, which was right outside of Las Vegas. Kind of amazing.
Yeah, that's really clever. Good way of harnessing the sun, because you don't need the solar panels. They had that.
Yeah, so the
photovoltaic cell.
Solar panels are more expensive to make than a mirror, and so this is a way to harvest a lot of energy, but it has to be pretty big. You remember that aerial shot? I mean, this was a huge, huge area that was covered in mirrors.
It was like a whole football field worth of mirrors.
You couldn't set one of these up in your backyard and boil water to 500 degrees Celsius. You need a lot more mirrors than that.
So this is kind of like the idea of getting a giant magnifying glass and trying to heat up one spot and get the water to boil that way. We're just reflecting it a different way than a magnifying glass.
Exactly. So we've covered 4 of our types of energy. Any guess what? Or no, we did 3. It's a good thing you're a math dad. You can count, right? What is our next one?
All right. So
our next one has to do with water.
Hydroelectric.
So our next source of energy we're talking about has to do with dams. A dam across a river blocks water. And one of the biggest in the US is Hoover Dam, which is really close to where we live. So this is a time lapse, and at nighttime, it's kind of hard to see the lake right behind the dam, but down at the bottom, you could see the water coming out. I'm going to play that one more time because it's a pretty short clip. And look at the water coming out of the dam at the bottom. That's where the river is. And then up above the dam, you have a lake. And in this case, with Hoover Dam, the lake is called Lake Mead. And Lake Mead is an enormous reservoir, and this works by gravity, really. Because gravity wants things to go down. And when you have this much water up behind the dam, that water is then going to push out the bottom with a lot of power. And then you use that power to
spin a magnet.
Spin magnets. And these magnets are really big. I'm going to show you a picture that Math Dad took. Never mind. Math Dad, it didn't make it in. So you just have to tell him how big were these magnets, because he went on a tour and saw the inside of Hoover Dam.
Bigger than the room that we're in, like huge, 30, 40 feet across, and it's big turbines that the water goes through. Really,
really big turbines and magnets. The advantage with hydroelectric power is that it can be turned on anytime. As long as you have water behind your reservoir, You can turn on that turbine anytime that you need it and get power. It doesn't have to be daytime. It doesn't have to be windy. It can happen anytime.
That's a huge advantage. So I know most of the power created at Hoover Dam actually heads off to California, but the energy grid can only support so much energy, and sometimes they can get too much. So the hydroelectric power has the advantage that they can crank it up or turn it down and do a lot of the fine tuning that will keep things powered but not overpowered, because too little or too much power is not good for the energy grid.
And the disadvantage is that eventually behind that dam, you have little bits of sediment being dropped, and eventually a dam can fill up with sediment and with dirt. And then what do? Is it going to take more energy to scoop all that dirt out now that the river has filled up the lake? That's something that's not going to happen to Hoover Dam for several hundred years. That's a problem that is a long way in the future, but it still is an issue. And it also disrupts the natural way that a river works. So some people say that, we should leave the rivers to have them be free, but a reservoir is a great way to store water, and it is a really clean source of power. We're not producing any pollution or emissions. So those are the advantages of hydroelectric.
But we're also in the middle of a drought. Every year, the lake level has been dropping for the last few decades, and the trend can't go forever, or we're out of water.
That's true. It's true. And with all of our energy sources, there's no such thing as a perfect energy source. Everyone has advantages and disadvantages. And let's talk about maybe one of the most interesting of all, nuclear power. So this is an aerial shot of a nuclear power plant, and you can see those big reactors. They are enormous. And what do you think that gas is coming out of the top?
Oh, no. If it's nuclear power, is it something dangerous?
It's water. It's steam.
Oh.
Steam coming out of the top. So the way that a nuclear power plant works, this is that little graph that we showed you at the beginning when we were talking about a coal-powered plant. Same exact idea, but look inside this chamber. We have control rods. These are made of uranium. And when uranium is around, it is a radioactive element. It's actually going to split apart. The atom is going to split in half. And when it does that, it causes a chain reaction and makes other atoms split apart, and it produces a lot of heat.
Oh, wow. So it's still heat and trying to make steam.
Yes, and they're heating up that water and making steam, and then using that to turn a really big magnet to create electricity. But with uranium and a nuclear power plant, it's incredible just how much energy can be produced. I want you to take a guess, Math Dad. If we have a thimble-sized rod of uranium, so something about that big.
Okay.
A thimble, like the size of my thumbnail.
All right.
How much coal would that be equal to?
Ooh.
If I'm going to burn, use up a thimble size full of uranium versus coal, how much coal would I need to equal one thimbleful of uranium?
Is it like a truckload?
It's a ton. 2,000 pounds of coal is equivalent to just a thimble-sized piece of uranium. So
it's really efficient then.
They're really efficient. They produce a lot of power, but the disadvantage is that they create waste. They create radioactive waste that then has to be stored somewhere. We live in Nevada, and anytime people talk about putting nuclear waste into Yucca Mountain in Nevada, everybody here says, no, 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 not in my backyard. The problem is nobody wants nuclear waste in their backyard, but it has to go somewhere.
Yep. And Nevada is somewhere, apparently.
Nevada is somewhere.
All right. So I've got a question for you, Science Mom. You're talking about all these energy sources. What does this have to do with Earth science?
Well, this has a lot to do with Earth science, because if you look at the amount of energy we use, it has increased a lot in the last few years. And remember how I said every single energy source has its side effects? Well, the amount of energy we use, if we are burning carbon fuels, and 62% of the energy produced in the US comes from burning natural gas and burning coal. That's producing a lot of carbon dioxide gas. And next week, we're going to talk a little bit more about climate change and what all of that pollution does. But producing gas and producing pollution, this is a common side effect of a lot of energy production. This can be a really big deal. And to understand just how big of a deal it is, I want to talk really quickly about the smog of 1952 in London. You ready for a crazy story, Math Dad?
Yeah, 1952.
So London is a city that is located in the United Kingdom, and it's in a climate that is close to the ocean and very humid. And in the year 1952, almost everybody in the city of London, the way that they heated their houses was with coal or a wood fireplace. But burning coal was the most common. And when you burn coal, you produce sulfur dioxide and ammonia. And those compounds, combined with the fog, created a smog that has been nicknamed the killer smog of London. It was so thick that during the day, noon during the day, you couldn't see more than 10 feet in front of you.
Oh, wow.
Can you imagine going outside and trying to walk down the street and you couldn't see more than just a few feet in front of you because the smog was so thick? They estimate that more than 10,000 people died just because of how bad the air was to breathe. It was a horrible disaster, and it was caused by so much people burning coal in such a small area. And then when the weather changed and the air wasn't being blown out to sea, it was just collecting there, and it got really cold, so more people were burning coal. That caused a big problem. Now, that is one extreme example of really bad pollution, but as a species, how we're producing energy and how we're using it has a really big effect on the planet.
Yeah, we've got to take good care of this planet. It's the only one we've got, right?
We do. We definitely do. Now let's do our Where in the World mystery, and then I've got some birthday shout outs, and we will go to our quizzes. So for our Where in the World mystery, we are switching over to cities. We had several that were about ancient ruins and abandoned places, but now we're talking about cities that are inhabited currently.
All right, I'm going to get it.
I think you'll need the help of the chat, Math Dad.
All right.
So this is next to a famous volcano. It's a city that is famous for cherry blossoms, and it has a population of more than 36 million people. That is your biggest clue.
What in the world? 36 million people.
The volcano and the cherry blossoms are also good clues, but the 36 million plus people is a pretty big clue.
All right, I think I know what it is from that clue. 60% chance. There's a lot of cities in the world, but 36 million people.
Coaster Cody has it. It is Tokyo. And Pickle Obsessed and Finn, I'm seeing several people say Japan. You are correct.
Tokyo has 36 million people?
It actually has 37.5 million. I looked it up today, but that's that's only in the city proper. If you include the metropolitan area outside, then it's even higher. And trying to decide where exactly is the city, like what's the boundary of the city, that can be kind of tricky because sometimes it just goes and goes and goes and kind of merges into other cities. But Tokyo is enormous and a beautiful city. And here's a picture where you can see Mount Fuji in the distance. That is one of the world's larger volcanoes, always snow covered. And then here is a cool time lapse just showing you how busy Tokyo is. So this is a main intersection in downtown Tokyo. You can see a time lapse of the traffic going by and then the pedestrians crossing the street. There are a lot of people in this city. I like
those corner-to-corner crosswalks. That's kind of fun.
The corner-to-corner crosswalks really are great. And then, Matt Dad, while you're getting the polls set up, I've got birthday shout-outs. On Wednesday, we forgot to do birthday shout-outs because I was so flustered by the fact that we had a massive computer crash right before we went live, and it threw me off. So first, a couple belated birthday shout-outs. A very happy birthday to Kayla, who turned 10 last Saturday, and a happy birthday to Ella, who just turned 10, and to Luca, who just turned 7. Happy belated birthday, you guys. And to Christian, who turned 13 on Tuesday. Happy birthday, Christian. And then tomorrow, Arushi has a birthday. Happy birthday, Arushi. Isaac turns 11 tomorrow. Happy birthday, Isaac. And Daniel from North Carolina turns 10 this Sunday. We hope you have a fantastic birthday, Daniel.
All right, getting older every day, guys.
Are you ready now for our quiz questions?
So I want you to go to itempool.com/sciencemom/live.
And if you're watching the replay on our website, you can participate in the polls too. But even if you're not clicking the buttons, I hope you will answer. See if you can beat Math Dad.
Look down in the description for the link. All right, our first question. True or false? Solar panels won't work in winter because they need to be warm to produce energy. And we did cover this one today. And I don't know if I knew this answer before Science Mom told it to me, but I do know it now. I'm guessing from that enormous bar that is going across above my head there that most of you are getting the answer right. So do solar panels work in the winter or not? Or
let's reveal the answer.
True or false? And the answer is false. Well done on this one, chat. Didn't stump them here. So the solar panels just need the light energy, and that's what they're converting. They're not using the heat at all.
You know what I just realized? We have an awesome experiment that we didn't do. Math Dad, if you'll go microwave that real fast, I'll go through the next couple questions.
Right. And I think you have a story to tell about a building with
all right.
windows shaped a certain way.
I do. A thimble-sized pellet of uranium can power as much as 2,000 pounds of coal. Is this true or false? That is our next question. And cool little fact about solar power. In Las Vegas, there was a building where the sides were really reflective and it was curved. And it was right above a swimming pool. And after they built the building, several people complained that they got really severely sunburned within just a few minutes. And they realized that the building was acting like a giant magnifying glass. And at certain times of year, it would focus all of that light down on the swimming pool. They had to redesign the whole entire building. So that was my crazy true story about solar power. And good job, you guys. This is true. Nuclear power is very, very effective. Next question. In 2019, 62% of the energy produced in the United States came from, and then it's up to you. Pick which one is the answer. Is it nuclear power, solar power, hydroelectric power, fossil fuels, or wind? Which of those produced most of the power in the US in the year 2019? What do you think, puppy? The puppy says that he has faith in you. He knows you were listening. He knows that you know the answer. Yes. And fossil fuels had the most votes, and fossil fuels is correct. Most of our energy came from fossil fuels. The next most common was nuclear power. Nuclear was about 20%, and then after that you had renewables. Nicely done, you guys.
Wait, I didn't stump them?
You did not stump them yet.
All right. This next one will be the one.
You can hope.
All right. Oh, no, this won't be the one. But okay, which of the following are renewable energy sources? We've got wind, hydroelectric, nuclear, oil and coal, solar. And I got to say, the idea of renewable energies is just so cool that you've got something where you're not using it up and it's gone, but yeah, it's still around and it's something that can be used again.
It really is a great concept.
I'm seeing 3 categories, got a lot of votes here.
All right, let's finish and reveal.
All right. And wind, hydroelectric, and solar are all correct answers.
Good job, you guys.
Now, hydroelectric didn't get quite as many votes. I guess it's, in some sense, a little less renewable.
Yeah.
I don't know. I mean, it might not be quite as friendly, but
it does depend on how you define renewable, but typically that is included when we're talking about renewable resources. Yeah. Next one.
All right, our last question.
You better hope it was a tricky one, Math Dad. Otherwise, going down.
This will stump them for sure. So, when were the fossil fuels made? 2,000 years ago, 40,000 years ago, 1,000,000 years ago, or 300 million years ago? When were the fossil fuels made? What do you think, Kaladin? Did you tell the story?
I did tell the story of the unintentional huge magnifying glass on a swimming pool that is what happened to a building. So they were harvesting a lot of solar power, but without realizing it. And it was all being focused down on a swimming pool. And several people got burned really badly. There was a lawsuit. The building got changed. It was a little bit of drama for this particular building. Let's go ahead and finish and reveal.
It'd be hard to anticipate some of those consequences. All right. And I stumped him here because...
You did not stump them.
Oh, I didn't stump them.
Good job, you guys.
300 million years ago.
This is the Carboniferous period. This is back before the dinosaurs. That's where most of our natural gas and gasoline and oil comes from. But to produce additional natural gas and oil, it's estimated that it would take at least 50 million years. That is a long time. Like that's the shortest amount of time.
So why do they call this the Carboniferous period?
Because it's the source of most of our carbon fuels.
So there just happened to be a ton of plant matter.
And the most important detail is that funguses like mushrooms, they had not yet figured out how to digest wood and cellulose. So all that plant matter was not being digested by funguses.
So the tree would die and the wood would just stay there.
It would not decompose, correct.
Oh, and then that built up over millions of years, and then that provided enough carbon that over time that turned into oil.
That's right.
So when we say that it's not renewable, we mean it's not.
It's really not renewable. All right, you get to try and do a dance with the puppy. Victory dance.
All right, or defeat dance.
Defeat dance.
All right, here
goes.
Victory
for the kids. Calvin's like, what is going on?
I don't know if you like that. But...
Sorry, Cal. All right, I want to show you guys real quick this Stirling engine. This is so awesome. So I have an engine here that is not going to produce any fossil fuels or burn any fossil fuels. It's not going to create any pollution. All that I need to power it is a difference in temperature. I need this bottom plate to be hotter or cooler than the top plate. And if I change the temperature of this bottom plate and make it hotter, then gas underneath this little lever is going to expand and push this little foam pad up. And then it will drive this piston up, which will then in turn push this little foam pad back down, and it will just keep going and going. Let's give it a try and see if it works. So I'm placing it on my little container of hot water right here. And I need to give it maybe about 10 to 20 seconds to get it warm enough. And then I'm going to give it just a tiny little bit of a spin. And if my engine is working, it will keep spinning and spinning, and it should even speed up a little bit. So think it'll work, Math Dad? Cross your fingers.
So the engine should spin the wheel. That's what.
Yep.
That's what we're accomplishing here.
That was not enough of a spin. Oh, come on. It was working earlier. It might not be warm enough yet. Did you get this water nice and hot, Math Dad?
Put it in the microwave. Uh-oh. If you can reach in and touch it, maybe it's not hot enough.
It's pretty warm. It's pretty warm. We probably just need to give it a slightly longer amount of time. And then while they're starting, we'll let it sit for just a minute. Let's look at the notes, and then we'll come back.
All right. Can I go microwave it again? Yeah. I want to make sure it's nice and hot.
You want to make sure it's nice and hot?
Yep. Sorry, I'll get you into the notes here, Science Mom, and then I shall return. Maybe.
Uh-oh.
The iPad will unlock. Come on, iPad, do your job.
You can do it, Math Dad. I believe in you. But I don't believe in our iPad, apparently. Technical difficulties. Oh, no. At least we have...
Got this. Oh.
There we go. We did it. All right. Math Dad's going to go and microwave that real fast because this little demo is pretty amazing, and we really hope that we can get it to work for you guys so you can see it. But then real quick, I just wanted to say that our prompt on page 40 is for you to invent a new energy source. So come up with an idea for a new source of energy, draw and describe it here. And if you want to share it with us, you can email it to us. We would love to see your ideas. So that's the little prompt there. And then one more important note that I wanted to make about this page. This should say Carboniferous, but there was a typo in the first version of the notes. I believe that this letter, instead of being an I, was something else. And I didn't want that to stump anybody when you guys were filling out the worksheet. So Carboniferous is the answer there. That is the period when our fossil fuels were produced. And now I'll come back to this main view and answer a couple questions while Math Dad is microwaving our water to get it ready. So, I see Remington Wolf. Why doesn't the boiling water freeze in the cup? I'm not entirely sure what that is referring to, but maybe clarify and ask again. Pickle Obsessed. Why are solar powers usually blue and not black? Because black picks up more heat. That is a great question, and I would have to do a little bit of research to answer it. My guess is that it has something to do with either the materials that are needed to produce the photovoltaic cells, and I think the color is dark enough that it probably absorbs just about as much heat as black does. But remember, they're most efficient when they're not overheated, so that might be a factor as well, that that's probably dark enough that they're absorbing lots of light but not overheating, because when they overheat, they're not going to be quite as efficient. And another good question. Yesterday there was a rover that landed on Mars. What powered that rover from Diamond Star? I hope that you guys all got to participate and watch a little bit about the rover landing. And if you didn't, you can see some excellent recaps on NASA's website. So what powered the Perseverance rover as it was landing? It's got several different sources of power. And I would have to do a little bit of research to be sure that I had accurate information for you on all of those.
I mean,
but it's got
my guess is it's long term. It'll be the solar power that continues to renew for it, because that's the one thing that it could take with.
But some of the craft that we've sent to Mars have had small little nuclear power operations as well, because that's one of the most efficient. Size for size, you can get a lot of power out of nuclear power. All right, let's see if our little Stirling engine will work now, because this is really an awesome little device. So our water is much hotter here now at the bottom. And if we can get this bottom plate to be warmer than the top plate, then I should be able to give it just a tiny little spin up here. And then it will start going and keep going on its own.
All right.
Cross your fingers.
You can do it, Science Mom.
Yes. Oh, wow. There it goes.
Wait, is that just from your spin, or is it?
You saw before, when I did a spin, it didn't just keep going and spinning. If it's just my spin and there's not a temperature difference, it's going to spin and then stop. And listen, it's speeding up.
It is.
And you can see that plate.
Ooh, we're actually getting a really cool effect right now where the frame rate is kind of matching up with the spin.
It is. The spin.
It looks like it's spinning slowly, but it's actually spinning much faster than that. It's only... Okay, so what's happening is with the video, they're getting like 30 frames per second. So like 30 pictures, and it's just flashing them across the screen. That's how a video works. But right now, it's as it stacks those pictures, by the time it gets to the next image, the wheel has moved far enough that you're not even seeing much motion, because those spokes line up regularly in their pattern. So yeah, we're getting some weird effect where it looks like it's spinning slowly,
but it's going really fast. You can see from that little turbine going up and down.
Yeah, it's one of those rare times when a camera...
Isn't that cool? Let's go back to this view.
Cannot capture what's actually happening very well.
So if I hold it right here, it'll take it just a few minutes to slow down, but it's still going because this bottom plate is warmer than the top plate. And these, when they were first invented in 1816, they thought this is going to be the engine of the future, because it can produce quite a bit of power. All you need is a difference in temperature, so you could put it lots of places. But to get the type of power we want for something like a car, this engine has to be a lot bigger than a gasoline-powered engine. But there are certain places where they use them, and one of the coolest is in submarines. Because a nuclear-powered submarine, you don't want to have an engine on there that's going to be producing gas, because then you can't be sneaky under the water. You're going to be leaving a trail of bubbles, right?
Right.
But if you have a Stirling engine next to your reactor, which is producing heat, and then one of the plates is on the outside where it's cold, you have a natural source of heat where you can power an engine that is completely clean.
Wait, are you saying it works with cold water and not hot water?
As long as you have a difference in temperature. So you need to have something cold on the top plate, something warm on the bottom plate, or
Vice versa.
could, yeah. So in fact, if you put this over ice and your top plate is really warm, it will work just how it did putting it over the hot water here. But you just need to have a big temperature difference. And cool fact, if it's over ice, it will spin the reverse direction.
Oh, that's cool.
So instead of spinning this way, it will spin that way. Isn't that awesome?
That is way cool. Where did you get this? Or is this something that
I ordered this online. Yeah, this little demonstration kit of a Stirling engine you can find on Amazon and lots of different places. If you search Stirling engine, like sterling silver, it will come right up. 3 quick questions that I want to answer real fast. One great one was from Amy. What is the best way to get energy from Earth? This is actually a really complicated question because, as we mentioned in the beginning, every single energy source has advantages and disadvantages. So I would argue the best way is probably to have a mixture of different types and then have them all go into a power grid. And then you're not relying just on one type. But certainly we want to shift and do more renewables. But I bet the best energy source has not been invented yet. I bet there are energy sources that we can invent in the future that will be better than what we're using now. And then LaFawn Raymond asked, what happens if a nuclear power plant explodes?
Oh, wait, man. So
Oh, sorry, Matt.
No,
Sorry, Matt,
no, we were good. I just panicked all of a sudden.
What happens if a nuclear power plant explodes? Bad things. So they call it a meltdown, and a meltdown can be catastrophic. Fortunately, it has not happened very many times. But if you have a nuclear power plant that is managed well, the risks are very low, and it is a safe place to work. That was another question that was in there. But if a nuclear power plant is not managed well, then it can be incredibly dangerous. So it all depends on how it's managed.
Well, in Japan, I think it was well managed, but they had a big
Had an
earthquake at Fukushima plant, and the earthquake did not manage the power plant very well.
And then last question from Kara: how big is the Hoover Dam? The Hoover Dam, do you remember, Matt, Dad? I think it's 800 feet high or more. It is really large.
Yeah, it spans at least a quarter mile there. It's covering a huge gorge, and it's really thick. In fact, it's like 10 times thicker than it needs to be, because they really wanted to over-engineer it so that the public wouldn't have as many concerns about it. And you might have even noticed they put all the administrative buildings down at the bottom just to say, hey, look, we are this confident that our dam is safe. We want to reassure you that that's the case. Yeah,
down here at the bottom, those buildings and windows that you see down there, that's where the people that work at Hoover Dam, that's where they work. They actually work down at the bottom of the dam. And that was sort of their way of saying, like, look, we're confident this is going to work. All the people who built and worked on the dam and are running it, they're going to have offices right here just to show you we are sure this is not going to break. Kind of a cool fact.
Yep.
All right, we are out of time. I hope you guys enjoyed this lesson. And next week, we have a fun activity on Friday. So our Friday activities, usually on Fridays, we do an art lesson or a project, but there are a couple Fridays like this one where it's a regular lesson. This was one of those. Anything else you want to say, Math Dad?
I just loved the quad dramas that you guys sent in.
Oh, we've had so much fun
to see all the work that you put into them, and some of the imagination from swinging monkeys and really cool color schemes and themes. So
yeah, nicely
way
done.
to go. Keep it up.
Work hard, grow smart. We'll see you next week.